Testing out the audio real quick. Got to go in and make sure YouTube's on the proper playlist and stuff like that. And I will get everything started. Hopefully DLive was going to work out properly. There we go. It's up. DLive is up and running. Good. YouTube is streaming by the looks of it. Audio sounds good on DLive too, by the way. Okay. YouTube is up. Sounds good. Testing Rumble here in a second. While that's getting loaded and everything, I can get this straightened out with Weird Science or with YouTube. So got that on live stream in the live stream playlist on the Wonderful World of Weirdness. Let me see what's going on there. Okay, so Rumble sounds good so far. Okay, so we got that straight. We may have to hit refresh on our kick. There it goes. It's on there. Okay, sounds good on kick. Is Twitch up and running? Looks like it is up and running good. So we got everything going. We are streaming on Kick, or no, on Rumble, Twitch, Kick, DLive, and on YouTube. So we're good to go. Now, before we get started, I want to let everybody know again that I do have a cold, and you got to excuse me when it comes. It's bad enough I can't read very well, but now I've got a bad cold to go with it. So everything is up and running and ready to go. So let me take a drink of my coffee real quick, and we will get to the topic. First, I got to make sure my topic is even up and ready to go. Yeah, actually, let me pull the topic up. That would be important, wouldn't it? Or the story, my stories, whatever you want to call them. Let me see. Yeah, my topics. All right. Yeah, so today is Weird Science, and I am going to let you guys know before I get started, too, that I'm finishing up with the last story that pertains to what I was discussing in my last episode. I wanted to go over like the history of the calendar and time and stuff like that, timekeeping and things of that nature. And I have one more article that I really do want to read to you guys about that, and then I'm going to be switching off to a different topic. So just to let you know that it's not going to be all about, the same basic thing. So it will be switching off. I still didn't get a drink of my coffee. All right. So there we go. So here we go. I will do my introduction and shut up and be done with it. So, hello, everybody, and welcome to another episode of Weird Science. I'm Roger Hanson, and I will be your host for today. I am coming back with more, or one more topic, one more story concerning the calendar and time, the history of timekeeping and things of that nature. And then within this episode, after this first topic is done, I'm going to switch to um a different area. So I wanted to let everybody know that ahead of time before I started getting into my talking points, and just to give a fair warning, you know what I mean? Now, we are streaming on Rumble, Kick, D Live, Twitch, and YouTube. So if you guys want to check us out, you can check us out on those platforms. And with that, I'm just going to go ahead and get into the stories. Now, before I get into the stories, I do want to tell you guys that I am sick. So just take that into consideration when I'm reading. If you hear me sound weird or anything, it's bad enough I can't read too well. But now I'm also sick on top of it. I didn't expect myself to, or I didn't really expect to be able to make it through to Sunday, to be honest with you. That's how bad I've been feeling. So this is actually really strange that I'm able to show up on Sunday and give this stream or do this stream. So with that, I will now get into the topic. The Great Year is an ancient concept rooted in both astronomical observation and metaphysical tradition. In its most basic scientific form, the Great Year refers to the time it takes for the Earth's axis to complete one full cycle of precession, a slow and continuous wobble in the Earth's rotation. This cycle, known as axial precession, takes approximately 26,000 years to complete. During this period, the position of the celestial poles and equinoxes slowly shift in the sky, causing a gradual change in the backdrop of stars against which the Earth aligns at different times of the year. Ancient cultures, particularly those with strong astronomical traditions, such as the Egyptians, Babylonians, Greeks, and Hindus, observed this long cycle and often imbued it with profound symbolic meaning. For the Greeks, especially through the writings of Plato, the Great Year was not only an astronomical cycle, but a philosophical one. In the dialogue Timaeus, Plato suggests that the return of the stars and planets to their original positions marked a kind of cosmic renewal, a moment when the heavens realigned in perfect harmony. This idea was later developed into a belief that all of history moves through vast cycles or cyclical epochs, repeating or rhyming in structure across the ages. In India, the concept of the Great Year closely parallels the idea of the Yuga cycle, a grand succession of ages that mark the rise and fall of spiritual and moral conditions in the world. According to Hindu cosmology, a full cycle comprises four yugas: the Satya, the Yuga, the Treta, four yugas: the Satra Yuga, Treta Yuga, Vapura Yuga, and Kali Yuga. Each yuga becomes progressively shorter in duration and more degenerate in character, with the Kali Yuga being the current age, marked by moral decay and spiritual ignorance. After the end of the Kali Yuga, the cycle begins anew with the Satya Yuga, a golden age of truth and enlightenment. Although the Yuga cycle operates on its own timeline, some traditions have tried to correlate it with the precessional Great Year. In esoteric and theosophical traditions, the Great Year is viewed not merely as a mechanical astronomical process, but as a metaphysical pulse that influences the rise and fall of civilizations, the evolution of consciousness, and the manifestation of divine order. Each phase of the Great Year is associated with change in human awareness, cultural values, and spiritual orientation. For instance, some theorists claim that humanity moves through ascending and descending arcs of spiritual enlightenment that corresponds to the 12 zodiacal ages created by the precessional motion. Each zodiacal age lasts roughly 2,100 years, and their succession forms the broader cycle of the Great Year. Excuse me. The age of Pisces, believed to have begun around the time of the rise of early Christianity, is often associated with faith, sacrifice, and dualism. Many believe that this age is ending or has already given way to the age of Aquarius, a period said to emphasize reason, community, innovation, and individual awakening. This transition is frequently interpreted symbolically as a shift in collective consciousness, not just a technical adjustment of celestial coordinates. This zodiacal framework suggests that each age influences the time of art, religion, politics, and science that dominate human experience. For example, the age of Taurus, thousands of years ago, was associated with bull worship in the agrarian civilizations of Mesopotamia and Egypt. The subsequent age of Aries emphasized conquest and patriarchal authority, reflecting the rise of empires and warrior deities. The age of Pisces, with its fish symbol and emphasis on spiritual suffering and salvation, has been shaped by Christianity and related belief systems. The age of Aquarium is expected to break down rigid institutions and foster a decentralized collective form of spiritual and social development. Philosophers, astrologers, and mystics have long debated whether the Great Year operates deterministically or whether human beings play an active role in shaping how its cycles unfold. Some interpretations suggest that the Great Year reflects the collective karma of humanity, a feedback loop between cosmic forces and human action. Others argue that it acts like a celestial clock, marking time but not dictating events. There are also interpretations that blend these views, suggesting that while the broad contours of the Great Year are fixed, the specific expressions of each age depend on human consciousness and free will. There are also theories, some speculative and others based on alternative history, that ancient civilizations may have possessed knowledge of the Great Year and encoded it into their architecture, myths, and calendars. Advocates of this view often cite structures like the Great Pyramid of Giza, the Temple of Angkor Wat, or the stone alignments of Göbekli Tepe as repositories of astronomical wisdom. According to this theory, the ancients were aware not only of the yearly solar cycle, but also of the much larger precessional cycle and its impact on human destiny. Others point to the myths of periodic cataclysms and golden ages found across cultures, from the Aztec and Mayan calendars to the Norse concept of Ragnarok and the Greek idea of successive ages of mankind as reflections of a shared understanding of long cosmic rhythms. These myths, while often symbolic, may represent humanity's attempt to grapple with cycles too vast to observe directly in a single lifetime. Modern scientific understanding confirms the existence of the precessional cycle, but does not attribute to it the metaphysical or historical significance claimed by many traditional or esoteric systems. In astronomy, the precession of the equinox is a measurable and explainable phenomenon resulting from the gravitational pull of the moon and sun on the Earth's equatorial bulge. It is used to track celestial change over millennia and calibrate ancient calendars. However, science does not support the idea that these cycles cause spiritual or civilizational shifts, regarding such claims as speculative. Throughout history, a number of thinkers have attempted to estimate the length of the great year, a grand celestial cycle marked by the full precession of the equinoxes, or in some cases, by planetary alignments or symbolic returns. These estimations have varied widely depending on the period, worldview, and tools available to those proposing them. Plato, writing in the 4th century before the Common Era, referred to what he called a perfect year in his dialogue Timaeus. He envisioned a vast cosmic cycle in which all the stars and planets would return to their original positions, but he did not assign a specific duration to this cycle. His perception was more philosophical and astronomical, focusing on the harmony of celestial movements rather than the empirical observation. Similarly, Cicero, who wrote in the 1st century before the Common Era, described the great year in terms of planetary cycles and alignment. Like Plato, he avoided offering any numerical figure and approached the idea as a metaphysical return of celestial order. Josephus, the 1st century Jewish historian, recorded that the ancient Chaldeans or Babylonians had a concept of a great year lasting 600 ordinary years. This number likely emerged from earlier Mesopotamian traditions, which were fond of numerical cycles and cosmic epochs, often based on sexagesmal systems. By contrast, Macrobius, a Roman writer from the early 5th century, cited that some ancient philosophers believed the great year to last 15,000 years. His source was likely symbolic, reflecting an ideal cosmic harmony rather than a measurable cycle based on axial precession. Censorinus, writing in the 3rd century, attributed to Aristarchus of Samos a great year, lasting roughly 2,484 years. Though some scholars suspect this figure may have been a miscopy of 2,434 years. This value would have reflected a cycle of eclipse rather than a full axial precession, likely based on combinations of lunar and solar calendars rather than stellar motion. Oenopides, a pre-Socratic Greek thinker from the 5th century before the Common Era, defined a version of the Great Year lasting 59 solar years. This period corresponds to 730 lunar months and was mainly useful for predicting eclipses. His cycle was not about the stars or Earth's wobble, but about the periodic alignment of the sun and moon within a practical calendar framework. Hipparchus of Nicaea, who lived in the 2nd century before the Common Era, was the first known astronomer to detect and measure axial precession. Comparing his own star measurements with Babylonian records, he deduced that the stars were shifting slightly over time. He calculated the precession at about 1 degree every century, which suggests a complete cycle lasting roughly 36,000 years. Though this was a rough estimate, it placed him among the first to approach the Great Year as an astronomical phenomenon grounded in observation rather than symbolism. Following Hipparchus, the influential astronomer Ptolemy also adopted a Great Year of approximately 36,000 years. Writing in the 2nd century of the Common Era, Ptolemy preserved and elaborated on Hipparchus's work, and in his seminal treatise known as the Almagest. His estimate, though similar in form to his predecessors, may have also been influenced by prevailing cosmological beliefs that place the heavens within a static, unchangeable framework reinforced by numerological harmonies. Throughout the medieval period, estimates of the Great Year were often symbolic, inherited from classical sources without empirical reevaluation. Some sources gave values such as 24,000 years, while others retained the 36,000-year cycle. None of these were based on rigorous measurements of axial movement, which would only become possible again with the advent of modern telescopic observation. In the modern period, scientific astronomy has provided a far more precise estimate for the axial precession of Earth. According to contemporary calculations, the complete cycle of precession in which the Earth's axis traces a full cycle in the sky, lasts approximately 25,700 years. This value has been derived from detailed observations of star positions combined with sophisticated understanding of Earth's rotational, mechanical, gravitational interactions and the forces exerted by the moon and sun. In the early 20th century, esoteric writers such as Rene Guénon, whatever, Guénon, Rene Guénon proposed spiritual interpretations of the Great Year. Guénon suggested a full cosmic cycle lasting 64,800 years. This number was not based on astronomy, but rather an adaptation of traditional Hindu yuga cycles, adjusted to fit his metaphysical framework. In his view, this cycle represented a gradual degeneration and eventual renewal of spiritual consciousness across the ages. Estimates of the Great Year span from symbolic and mythological to empirical grounded calculations. Plato described a perfect return of the celestial order without specifying its duration. Cicero echoed similar sentiments without figures. Josephus cited ancient Babylonian traditions that pointed to 600 years as a great year. Macrobius referenced a 15,000-year cycle from ancient philosophy. Censorinus recorded a shorter duration tied to eclipses, possibly around 2,400 years. Wanapides proposed a practical 59-year cycle, useful for lunar prediction. Hipparchus and Ptolemy both supported a value near 36,000 years based on early measurements of stellar drift. Modern astronomers now understand the cycle of axial precession to last nearly 26,000 years. Meanwhile, spiritual authors like Rene Guénon adapted ancient values to propose cycles over 64,000 years to fit religious and cultural paradigms. Okay, getting me some coffee. I have never had to actually stop and have a conversation in the middle of a stream before, but I'm going to tell you guys right now, this is something else. So, here we go. And like I said, I'm going from there to switch to another one that I needed to, or because I wanted to do that one before I moved on. The last time I was doing calendars, so I wanted to do that first before I moved into my new areas. Okay. Dimethylamine is a secondary amine that plays an important role in a wide range of chemical processes, medical developments, and industrial practices. This compound is particularly notable because it features two methyl groups that replace two of the hydrogen atoms typically bonded to a nitrogen atom. These substitutions significantly alter the physical and chemical behavior of the molecule, expanding its use across multiple disciplines. A full understanding of dimethylamine requires exploring its chemical behavior, environmental interactions, production techniques, health effects, and applications in modern industry. Amines are a class of nitrogen-based organic molecules derived from ammonia, where one or more hydrogen atoms are replaced by carbon-based groups. In the case of dimethylamine, it is considered a secondary amine, meaning that two of the hydrogen atoms attached to the nitrogen in ammonia are replaced by methyl groups. This substitution results in a structure composed of nitrogen atom bonded to two methyl groups and one remaining hydrogen atom. The geometry of this molecule is trigonal, pyramidal, with the nitrogen atom occupying the apex. The lone pair of electrons on the nitrogen contributes to the molecule's reactivity, ability to form bonds, and general chemical behavior. The replacement of two hydrogen atoms in ammonia with methyl groups brings about a number of changes in how dimethylamine behaves chemically. One of the most noticeable differences is an increase in basicity. Methyl groups tend to donate electrons towards the nitrogen atom, which raises the electron density and strengthens its ability to attract protons in chemical reactions. As a result, dimethylamine is more basic than ammonia. As a result, dimethylamine is more basic than ammonia. Another important characteristic is the presence of steric hindrance. The two methyl groups are relatively bulky, and their spatial orientation around the nitrogen atom makes it harder for other molecules to approach and react, especially in certain types of substitution reactions. In terms of hydrogen bonding, dimethylamine has only one hydrogen atom bonding to nitrogen, which limits its ability to form hydrogen bonds compared to primary amines. This has the effect of lowering the boiling and melting points and increasing the volatility of the compound. Chemically, dimethylamine is an effective base and a strong nucleophile. The lone electron pair on the nitrogen is readily available for bonding with electrophilic atoms, making it reactive in a variety of chemical environments. When introduced to an acidic medium, dimethylamines dimethylamine readily accepts a proton, forming a positive charged ion called dimethylaminoin. Di- dimethylaminoin. Minoium. Dimethylaminium. This ability to undergo protonation is key to many industrial acid-base reactions. The increased electron density on the nitrogen also enhances its capacity to react with electrophilic compounds. For instance, in alkylation reactions, dimethylamine bonds with alkyl halides to form tertiary amines, which are valuable in agriculture and pharmaceuticals. The acylation reaction, it reacts with acid. No, in acylation reactions, it reacts with acid-derived compounds to create amides, useful in both organic chemistry and polymer development. Due to its chemical structure, dimethylamine is very soluble in water. It can form hydrogen bonds through fewer than its simpler amine counterparts. Its boiling point is low, just above freezing point of water, which makes it a gas at room temperature under typical atmospheric conditions. However, it is easily compressed into a liquid for storage and transport. There are several standard methods used to synthesize dimethylamine, and the method chosen usually depends on the required production volume. One of the most common techniques involving reacting methanol with ammonia in the presence of a catalyst such as zeolite or alumina. This process creates methylamine as an intermediate, which then reacts further to form dimethylamine along with water as a byproduct. Another laboratory scale method involves reducing formaldehyde in the presence of ammonia, which also yields dimethylamine under the right conditions. The versatility of dimethylamine makes it indispensable in multiple industries. In agriculture, it is a key component in herbicides, pesticides, and fungicides. For example, one widely used herbicide is made from the dimethylamine salt of a compound designed to target broadleaf weeds, offering farmers a powerful tool for crop protection. In fungicides, dimethylamine provides the solubility and delivery of the active chemical agents, helping ensure even distribution across large planting areas. In the realm of polymer chemistry, dimethylamine contributes to the development of specialty materials such as ion exchange resins and modified polyacrylamides. These polymers are widely used in the treatment of water and in the manufacture of paper. When used in this context, or when used in these contexts, they, dimethylamine, dimethylamine, dimethylamine influences both the structural properties of the polymer and its interaction with dissolved substances. In the pharmaceutical sector, dimethylamine is vital for the synthesis of many drugs. It acts as a precursor in the production of compounds that relieve allergies, reduce nasal congestion, and provide local anesthesia. Its role is especially prominent in nitrogen-based compounds, where its presence in drug molecules often enhances therapeutic activities. Dimethylamine also appears in compounds used to treat pain, manage high blood pressure, and address a wide variety of chronic conditions. Its reactivity makes it a flexible tool for chemists developing new therapeutic agents. Water treatment is another area where dimethylamine finds practical use. Salts derived from dimethylamine are used during the purification process, particularly in flocculation and coagulation steps. These processes help remove suspended solids from water by encouraging the particles to clump together, making them easier to filter out. The result is cleaner water suitable for industrial or municipal use. Because of its effectiveness and relative availability, dimethylamine has become a standard chemical in many large-scale water purification systems. Although dimethylamine is primarily produced in industrial settings, it also occurs naturally in small quantities. It can be detected in the environment as a result of organic decomposition, especially in marine ecosystems where plants and animal materials break down. In humans, it appears as a minor byproduct of protein metabolism, although it plays no active physical role. In low concentrations, it is harmless, but larger doses can cause irrational or discomfort. It can cause irritation or discomfort, especially when inhaled. From an environmental perspective, dimethylamine is relatively persistent. It does not degrade quickly and can linger in air, water, and soil for extended periods. This makes proper handling important, particularly in locations near bodies of water where marine organisms could be affected. An accidental release or disposal must be managed carefully to avoid contamination. In terms of human health, dimethylamine is classified as an irritant. When inhaled its gaseous form, it can affect the respiratory system, eyes, and skin. Exposure to high levels over long periods may result in more serious health issues, including damage to the mucous membranes. Because of this, because of these risks, workplace environments that involve handling dimethylamine must adhere to strict safety procedures. Protective equipment such as masks, gloves, and safety goggles is essential, and the area should be well ventilated to prevent gas accumulation. These measurements help minimize the health hazards associated with routine handling of the compound. Looking towards the future, the role of dimethylamine may grow in both established and emerging sectors. With increased attention on sustainable practices and environmentally friendly chemistry, researchers are working to find new ways to produce dimethylamine using renewable resources rather than traditional fossil fuels. This would reduce its environmental impact and align production practices with broader global sustainability goals. At the same time, pharmaceutical science continues to explore new therapeutic avenues where nitrogen-based compounds like dimethylamine could be crucial. As new diseases emerge and treatments become more complex, the demand for versatile chemical building blocks such as dimethylamine is expected to increase. Dimethylamine is a compound of significant chemical, industrial, and environmental importance. Its molecular simplicity conceals a broad array of properties that allows it to function effectively in many settings, whether serving as a reagent in chemical synthesis, an active agent in agricultural chemicals, a building block of polymer production, or a precursor to pharmaceuticals. Its usefulness is widespread. Understanding how it behaves at the molecular level, recognizing the risk involved in its handling, and continuing to improve production and application methods will ensure that dimethylamine remains a valuable tool for science and industry. Its story is one of transformation and utility, built on the simple substitution of hydrogen atoms and extended into the complex network of modern human enterprise. Heptane is a straight-chain hydrocarbon composed of 7 carbon atoms and 16 hydrogen atoms. It is widely used across multiple industries due to its favorable chemical characteristics, particularly its non-polarity and volatility. One of its most well-known roles is as a benchmark in fuel testing, especially in the determination of octane ratings. Because of its tendency to ignite prematurely in engines, heptane serves as the reference compound against which other fuels are compared for knock resistance. Additionally, it finds extensive application as a solvent in laboratories, manufacturing processes in various industrial sectors. With growing concern over environmental sustainability, however, the applications of heptane's widespread use have come under increasing scrutiny. Chemically, heptane is categorized as a saturated hydrocarbon, meaning all of the bonds between its carbon atoms are single. This makes it relatively stable and less reactive than compounds with double or triple bonds, such as alkenes or alkanes. Though it has a simple linear structure, heptane exists in several isomeric forms. These branched versions differ in how the carbon atoms are arranged, but maintain the same overall chemical formula. Each isomer exhibits slightly different physical properties, which can influence their behavior in industrial or scientific applications. Physically, heptane is a clear, colorless liquid with a boiling point just below 100 degrees Celsius and a melting point near negative 90 degrees Celsius. It is lighter than water, with a density slightly below 7/10 of a gram per cubic centimeter at room temperature. Insoluble in water, it mixes easily with other nonpolar substances. These features make it an effective solvent for compounds like oils, fats, and waxes. Its low boiling point means it evaporates quickly, which is advantageous in processes that require rapid drying or the removal of solvents without leaving residue. In fuel research, heptane plays a critical role in determining octane ratings. These ratings measure a fuel's ability to resist premature combustion or knocking in high compression engines. Because heptane ignites easily under compression, it is assigned an octane value of 0. Its counterpart, a highly knock-resistant compound known as isooctane, is given a rating of 100. Blends of these two substances are used as reference fuels to calibrate testing instruments and determine the performance characteristics of chemical gasoline. High-performance engines require fuels with high octane values to operate effectively, and heptane helps define the lower boundary of this scale. Historically, heptane has influenced the development of aviation fuels as well. During the early to mid-20th century, engineers used heptane in combination with other hydrocarbons to experiment with fuel formulations for altitude high altitude aircraft. This research led to the production of fuels that allowed fighter planes to maintain engine power and reliability under extreme conditions. The insights gained through these experiments contributed directly to the aviation fuel standards that remain in place today. Beyond fuel research, heptane serves as a versatile industrial solvent. In organic chemistry laboratories, it is commonly employed during recrystallization, a process used to purify chemical compounds. By dissolving a mixture in warm heptane and allowing it to cool gradually, chemists can separate impurities from the desired product based on their different solubilities. This method is particularly useful in pharmaceutical research where purity is paramount. In pharmaceutical industry, in the pharmaceutical industry, heptane aids in the synthesis and isolation of various drugs. One example is its use in aspirin production. In one stage of the manufacturing process, heptane helps dissolve intermediates and facilitates the crystallization of the active compound. A case study from a European facility demonstrated that incorporating heptane in the final purification step increased product purity from 95% to over 99%. Because heptane evaporates quickly and leaves minimal residue, it ensures that the final medication meets stringent regulatory standards. Heptane also widely used Heptane is also widely used in the manufacture of adhesives and sealants. In industries such as shoe production and automotive assembly, fast-drying adhesives are essential for efficient workflow. Heptane's volatility enables rapid curing, allowing for strong and durable bonds without long wait times. Similarly, in industrial cleaning, heptane serves as a degreasing agent for machinery and engine components. Its ability to dissolve oils without disturbing moisture makes it ideal for cleaning metal surfaces prior to assembly. A case study from Japanese automotive plants highlight the benefits of using heptane as a degreasing solvent. After switching to heptane-based cleaning systems, the plant reported a 30% reduction in degreasing time and improved overall efficiency. Corrosion-related defects also decreased, as heptane did not introduce moisture into the clean parts. However, the study also emphasized the importance of strict safety measures due to heptane's flammability. Despite its utility, heptane poses environmental and health risks. It is classified as a volatile organic compound, meaning that it can contribute to air pollution when released into the atmosphere. These compounds interact with nitrogen oxides in the presence of sunlight to produce ground-level ozone, a major component of smog. In areas where industrial emissions are high, this can lead to significant environmental and public health concerns. One incident that drew attention to heptane's environmental impact occurred in Texas, where a refinery spill released over 1,000 gallons of the compound into a nearby waterway. Emergency response teams worked to contain the spill using absorbent materials and mechanical skimmers. However, traces of heptane were detected in the local groundwater for months afterwards. raising concerns about long-term ecological damage. This event prompted the facility to implement more rigorous containment protocols and highlighted the need for better environmental safeguards. In occupational settings, workers who handle heptane must be protected from its vapors, which can cause dizziness, nausea, headache, and respiratory irritation. Prolonged exposure may lead to chronic health issues. In a study published by a professional health association, employees of a chemical plant who were regularly exposed to heptane showed increased rates of respiratory problems compared to their peers. Following this finding, the plant installed new ventilation systems and required workers to wear protective gear, which led to significant improvements in health outcomes. As concerns over sustainability grow, industries are exploring alternatives to heptane that pose fewer environmental and health risks. Green solvents derived from renewable sources are being developed to replace traditional hydrocarbons. These alternatives aim to maintain the effectiveness of heptane while reducing volatile emissions and fire hazards. Some are even made more agricultural. Some are even made from agricultural waste, offering both environmental and economic advantages. One paint manufacturer in Germany transitioned to using bio-based solvents in place of heptane. Within the first year of this change, the company reduced its emission of volatile organic compounds by 40%. Workers reported fewer symptoms related to solvent exposure, and the quality of the paint product remained consistent. This success story has encouraged other firms to consider similar changes, providing that sustainable alternatives can be both practical and beneficial. Heptane is a chemically stable, non-polar compound that serves in numerous essential functions in modern industry. From its foundational role in fuel testing to its widespread use as a solvent in pharmaceuticals and manufacturing, it is a key component in many technical processes. Nonetheless, its volatility and environmental persistence require careful handling and regulation. As new technologies and materials emerge, heptane may gradually be replaced by greener solutions. Until then, understanding its properties, applications, and risks remain vital for those who work with or are affected by this versatile hydrocarbon. And, just reading through that, I can honestly tell you I don't see anything green replacing that. I just don't see it. You know what I mean? It's like heptane. Sounds horrible. Just putting it out there. You know what I mean? I wanted to put that do these readings in that order because I wanted to finish up on what I'd done in my previous video. Plus, I wanted to go into a little bit of the chemical aspects of some weird science that's going on in the world today. I have some other stuff too concerning chemicals that I do want to also add to this. I'm also wanting to get back to more of the techie stuff because I know a lot of people do enjoy that. But I want to do a fair share of um, the amount of weird science that's going on in the world today. So I want to do a shout out to Detective Fallen on YouTube, The Wonderful World of Weirdness, in the chat section. Thanks for stopping by, and thanks for making a comment in the chat section. If you guys want to um, find out more about Detective Fallen, you can find him on Discord. He has his own channel there, or server. It's called Home Away from YouTube. It's a pretty good place to go to, especially if you're a gamer and you want to watch, like, and comment WLCs. They still have that going on there, so go in there and you'll have people who can help you with your views and stuff like that. So check that out on Discord. And he's also on YouTube. He has his own channel, Detective Fallen. He's got some pretty cool stuff. So, that being said, I am going to say it again. We are streaming on Rumble, Kick, Twitch, DLive, and YouTube. On Rumble, you can find me at The Wonderful World of Weirdness, of course, and also The Wonderful World of Weirdness at The Wonderful World of Weirdness on YouTube. Now, on a Kick, you'll have to look at Roger_Hanson. That's the same with DLive as well. Now on Twitch, that's a different story. I am Infamous 1969 on there, and you can find me there. So if you like this video, please like, subscribe, share, make comments. Feel free to make comments, give feedback, say hello, just anything. If it's about the topic, it's cool. If it's not, don't worry about it. Just make a comment. You know what I mean? You really don't understand how much that's appreciated when people will reach out and say hi in the comment section. So just do me a favor, man. Leave a comment, and I will respond to every comment that's made. I've actually got a reputation of actually responding to people's comments. So, with that being said, I hope you guys enjoyed. If you did, hope you have a good night, good morning, good evening, whatever time of the day it is. And I am going to go ahead and end this stream. Thank you all for watching.